Good morning, students. Today we will learn the relation between the thermal coefficients of expansion. Relations between coefficient of linear expansion with coefficient of volume expansion. Relation between coefficient of linear expansion with coefficient of superficial expansion. So first we will learn the relation between coefficient of linear expansion and coefficient of cubical expansion, that is coefficient of volume expansion. What is the relation between alpha L and alpha B? What is the relation between alpha L and alpha B? So to learn that, let us consider a cube of volume B. Let the side length of this cube be L. So the volume of this cube is L cube. First we will learn relation between alpha L and alpha B. Consider a cube. Consider a cube of length L. A metallic cube of side length L. Each side is of length L, so that its volume before increasing heat, its volume B is equal to L cube. As we increase temperature to T plus delta T, as temperature is changed by delta T, if the temperature is increased to delta T, let the volume be increased by V plus delta V. So when it is heated strongly by raising temperature delta T, let the volume of this cube be V plus delta V. V plus delta V. This is the increased volume of the cube, right? When temperature is raised to delta T, let volume be increased by V plus delta V. Means when the temperature is increased from T to T plus delta T, let the increase in volume be V plus delta V. Let us say increase in volume takes place by increasing side length of each side. Increase in length of each side. Let increase in length of each side be L plus delta L. Let L plus delta L as temperature increases to T plus delta T. So for change in temperature delta T, change in length is delta L. That's what we are observing. Now we will have to calculate what is delta V. Delta V is change in volume. So we know volume is equal to L cube. So now change in volume. Change in volume we will calculate. Delta V. Delta V can be calculated as L plus delta L whole cube minus LQ, because before increasing the temperature, the volume of the cube is LQ. V equal to LQ. This is V, and later on it becomes V plus delta V. So delta V is equal to V plus delta V minus V. This is nothing but V plus delta V minus V, which is calculated as L plus delta L whole cube minus LQ. This is cube of increased side length, L plus delta L minus LQ. So if we expand this, we get LQ plus delta LQ plus 3L into L plus delta L. Using A plus B whole cube equation, we can write this minus LQ. So LQ cancels. When LQ cancels, you are left with delta LQ plus 3L square plus 3L delta L. Delta LQ plus 3L square plus 3L square delta L. 3 delta L I took is 3L delta L. Just correction here. 3L delta L into L plus delta L. It is like AQ plus BQ plus 3AB into A plus B. Yes. 3L delta L into L plus delta L minus LQ. Now LQ cancels. Now you are left with delta LQ plus 3L square delta L on expansion 3L delta L square. Now we are neglecting these terms of delta L square and delta L cube. Neglecting the terms of delta L square and delta L cube. Since delta L itself is very small change in length, it's a fractional change in length, right? So it's a fraction. When you cube that fraction, delta L into delta L into delta L becomes, it is still a smaller decimal, which is negligible. Similarly, delta L square is also a small decimal. So neglecting delta L square and delta L cube, we are left with 3L square delta L. Here delta L cube and delta L square are ignored, since delta L cube is very small compared to L cube, and delta L square is also very small compared to L square. So you are left with 3L square delta L. Therefore, I can write here change in volume is equal to 3L square delta L. Multiplying and dividing by L square. Multiplying and dividing by L. What do you get? Multiplying and dividing by L. L square into L becomes L cube. So it becomes 3L cube delta L divided by L. Now we know what is L cube. L cube is nothing but volume. So thus delta V becomes equal to 3V delta L by L. Now what we will write what is delta L by L from our previous knowledge. Fractional change in length. Fractional change in length, it is directly proportional to change in temperature. So we know that fractional change in length is equal to alpha L into delta T, where alpha L is coefficient of linear expansion and delta T is the change in temperature. So delta L by L is equal to alpha L delta T. Change in the fraction change in length is directly proportional to delta T. As a result, we can write fraction change in length is equal to coefficient of linear expansion as a constant of proportionality into delta T. So I can replace this in this equation. So thus we get delta V is equal to 3V into alpha L delta T. Alpha L delta T. So let me write this on the other side so that it will be clear. Thus you can see here delta V equal to 3V alpha L into delta T. Now we will take this V and delta T to the left hand side. What happens? Delta V by V into delta T becomes equal to 3 into alpha L. But what is this? Delta V by V into delta T. This is nothing but fractional change in volume per unit rise in temperature. This is nothing but alpha V. But change in volume per unit rise in temperature is equal to alpha V. Therefore, I can write this LHS as alpha V. Alpha V is equal to 3 alpha L. So this is a very important relation. So this can be obtained by considering an example of a cube of side length L. Okay. In the same way, we can now relate alpha L with alpha A, coefficient of superficial expansion. Relation between alpha L and alpha A. Now here consider a square plate of each side L, a metallic plate of area A which is equal to L square. Consider a metallic square plate of each side L so that its area becomes L square. Now due to increase in temperature, let the area increases by A plus delta A. Let the area increase by A plus delta A. Let A equal to L square be the area of a metal square of side L. As temperature rises from T to T plus delta T, area expands. Area increases from A to A plus delta A. So due to rise in temperature delta T, there is a expansion in area delta A. So what is delta A can be now calculated. So delta A can be calculated as A plus delta A minus A. A plus delta A minus A. So that A cancels, you are left with delta A. What is A plus delta A? A plus delta A is L plus delta L whole square. As we have considered again earlier, as temperature increases from T to T plus delta T, consider the length of each side increases from L to L plus delta L. Length increases L to L plus delta L. So A plus delta A becomes L plus delta L whole square. L plus delta L whole square. Because A is L square. So A plus delta A becomes L plus delta L whole square. Minus A. A is L square. Now you can simplify. Expand this. We get L square plus 2L delta L plus delta L square minus L square. L square cancels. Therefore, you are left with 2L delta L, and again we are neglecting delta L square. Here, delta L square is ignored or neglected since delta L square is very much less compared to L square. Therefore, you are left with 2L delta L. Again, multiplying and dividing by L, we get 2L square delta L by L. Right? Thus, we get delta A is equal to 2L delta L, multiplying numerator and denominator by L, we get 2L square delta L by L. So that L square can be substituted by A. L square is equal to A. And what is delta L by L again? Delta L by L, as we have noted down earlier, is equal to alpha L into delta T. Alpha L into delta T. Right? Substituting this in this equation. Thus we get delta A. Delta A as equal to 2 times A into alpha L delta T. Alpha L into delta T. So thus, now you take this A to the left hand side, delta A by A, and even delta T also to the LHS. Delta T becomes equal to 2 times alpha L. And what is this? Changing area per unit area per unit rising temperature. This is nothing but alpha A, coefficient of superficial expansion. Here, delta A by delta T is equal to alpha A. Therefore, substituting this as alpha A is equal to 2 times alpha L. So this is the relation between coefficient of superficial expansion or aerial expansion. So we can see finally the relation between alpha B, alpha A and alpha L. We got alpha B equal to 3 times alpha L, alpha A equal to 2 times alpha L. So using this I can write what is alpha L. Alpha L is equal to alpha A by 2, alpha L is equal to alpha B by 3. Okay, this relation you can verify with the list already available with you, which we have made in the previous videos about the coefficient of cubical expansions or coefficient of volume expansions of certain solids like aluminum, brass, copper, iron. You can compare it with the same values of linear coefficient of linear expansions for the same metals. Coefficient of linear expansions for the same metals, that is of aluminum, brass, copper, iron, right? When you compare, then you will realize the relation between these coefficients. Okay, these are very important. Now we are going to I have one more exercise. That is, I am going to give this exercise for you to prove the same relation. Alpha A equal to 2 times alpha L. To prove relation between areal expansion and coefficient of linear expansion for a metal rectangle of length A and breadth B. Suppose there is a metal rectangle of length A and breadth B. I am giving this exercise for yourself. Try it. So that when the temperature changes from T to delta T, the length changes from A to delta A. Right? At the same time, the breadth changes from B to delta P. So if you draw this diagram, you will get changing area. Changing area is going to be in this way. Right? So using this rectangular method, of area A equal to AB. Prove that alpha A is equal to 2 times alpha L. I think we will be able to do this. I did it with the help of square. You can try it with the help of rectangular metallic piece, a metal rectangle. Okay. Now we will discuss one more very interesting and very useful application of linear expansion. If you actually observe the iron rails, the railway tracks, between two railway tracks there will be always some gap being left. Two railway tracks, two rails, when they are joined with some gap in between them, nearly half an inch or more than that. So much of gap is left, and then they will be joined. Means joined by sideways. They are joined by fish plates. They are called as fish plates. So purposely a gap is left, so that in the summer season the linear expansion of the iron rails take place due to heat. The whole day, lot of heat will be there due to bright sunshine. As a result, the iron rails tend to expand. So if we do not provide any gap, then what happens? These rails will have compression on each other due to expansion. When they expand on each other, they have compression on each other. They will have a thermal stress. As a result, they tend to buckle. Due to this buckling effect, it is leading to very dangerous accidents. Therefore, purposely a gap is left between two rail tracks, between two rails when they are joined. You must have observed. In the same way, even in the construction of bridges and all, you might have seen some gap being left between the beams. When the beams are joined, there will be particularly a gap is left, because even the concrete expands due to strong heat. Whenever you are crossing the huge bridge, you please observe there will be some gap. Kolar bridge you might have observed. In between there is a gap. So when your vehicle is moving, you will experience that gap. Or you can observe it from a distance. There will be certain gap so that the summer season it can expand. Purposely a gap is left so that it can expand, and there will be no thermal stress even for the concrete. And you might have a common observation. The electric lines between the poles will be found sagging will be found hanging in the summer season because of expansion. Because of hot sunshine, they expand. Therefore, purposely between the two poles, when they are connected, purposely they will be leaving little extra length so that they can expand, and in the winter season they can contract. So this is the application of the thermal expansion that we see in our day-to-day life. Practical application. Okay, let us see one example of thermal stress. Now we are discussing very important application of the thermal expansion, linear expansion. That is, what happens by preventing thermal expansion of a metal rod by fixing its ends rigidly, as just now I discussed with the rail tracks. When two rail tracks are joined together, then there will be purposely a gap is being left between two rails when they are joined length to length, right? If these rails are not provided any gap, if these rails are covered by fixing its ends rigidly, if they are closely connected, then what happens? So this is what we are discussing. If the metal rod is now not allowed to expand, being closed by fixing its ends rigidly, then what happens? Due to heating effect. Due to heating effect, the metal rod tends to expand on either side. There should be a gap to be provided, or what happens? Then it tends to expand. As a result, there will be a compressive strain developed in the metal rod. Since the rigid ends will be exerting force on either side, the expansion is tending to take place linearly on either side. Since the rigid supports, rigid ends are exerting external forces which do not provide any expansion, so the metal rod experiences compressive strain on both sides. As a result of compressive strain, it will tend to have compressive stress. So the ratio of compressive stress to the compressive strain, we have learned it as Young's modulus. Recall Young's modulus, where we discussed the topic of solid mechanics, mechanics of solids. The ratio of the longitudinal stress to the longitudinal strain, the ratio of longitudinal stress to the longitudinal strain is called as Young's modulus. In the same way, when it is undergoing compressional strain due to compressional stress, in the same way we can define the Young's modulus as compressive stress divided by compressive strain. That is nothing but longitudinal stress divided by longitudinal strain. So which is F by A divided by change in length per unit length. That is what we are written as compressive strain. Stress by strain, that is Young's modulus. This is Young's modulus. So we can calculate what is compressive stress. Compressive stress can be calculated as F by A is equal to Y into delta L by L, where Y is Young's modulus of that particular rod. Suppose we have taken iron rod, then we have to substitute the value of Young's modulus of iron rod, and we can calculate this stress. This stress is called as thermal stress. The stress is compressive stress because of the heating effect. Since it is not allowed to expand, so it will be under compressive stress due to rigid ends. So compressive stress is also nothing but thermal stress due to heating effect. So what happens here? The metal rod suffers from compressive strain, experiences Compressive strain on either side. Due to thermal stress. Due to thermal stress. So thermal stress can be now defined as the thermal stress is a compressive stress that is developed in a metal rod when the metal rod is not allowed to expand, when its ends are being held by closed ends, when its ends are held closed ends by closed ends, then the thermal stress can be calculated. Now it depends on the thermal strain. Delta L by L is the thermal strain. Thermal strain can be calculated using the coefficient of the linear expansion. Just now we have learned in this topic. We have delta L by L is equal to alpha L into delta T. So delta T is the change in temperature. So by the knowledge of delta T, we can calculate, suppose the temperature is raised from 30 degrees Celsius to 40 degrees Celsius during daytime. Let us say it has been raised from 30 degrees Celsius to 40 degrees Celsius, so that change in temperature is 10 degrees Celsius. During this 10 degrees Celsius, we can calculate what is the fractional change in length. The knowledge of coefficient of linear expansion, which is a constant for that particular metal rod. If it is iron rod, we have to take alpha L for iron. If it is a steel rod, we have to take the value of coefficient of linear expansion of steel. So if you substitute in this equation, then thermal stress F by A now becomes equal to Y into alpha L delta T. Let us consider an example. Consider an example of a steel rod of length 5 meter. Steel rod of length 5 meter, right? And its temperature is raised by 10 degrees Celsius. Temperature is raised by 10 degrees Celsius. Length is 5 meter, and it's let us say area of cross section. Area of cross section is 40 centimeters square, where A is area of cross section. Area of cross section of this metal rod, 40 centimeters square. So you can calculate the thermal stress experienced by steel rod of length 5 meter when there is a change in temperature. If change in temperature is 10 degrees Celsius. As I said, let us say temperature is changed from 30 degrees Celsius to 40 degrees Celsius during daytime. How much is the thermal stress experienced? What is the value of thermal stress? Here we have taken into consideration of coefficient of linear expansion of steel. Coefficient of linear expansion of steel from the data, from the list, it is 1.2 into 10 to the power of minus 5 per Kelvin. 1.2 into 10 to the power of minus 5 per Kelvin. So now we can substitute all this. When you substitute this, we can get the value of thermal stress. So here Y becomes Y steel and alpha L is that of a steel. So you can just directly substitute Y steel is 1.2 into 10 raised to minus 5 into alpha L is okay, alpha L itself is this one. So we have to find out what is the Young's modulus of steel. Young's modulus of steel is also known to us. It is 2 into 10 raised to 11 Newton per meter square. Young's modulus of steel. It's given Young's model is 2 into 10 raised to 11 Newton per meter square. With this data, we can calculate what is thermal stress. We can write now Young's modulus 2 into 10 raised to 11 into 1.2 into 10 raised to minus 5 into change in temperature 10 degrees Celsius. Change in temperature 10 degrees Celsius is same as change in temperature in Kelvin also. Change in temperature in Kelvin is same as change in temperature in degrees Celsius. Okay. So delta T is equal to 10. So if you calculate this, then it comes out to be 12. 12 into 2, 24. 24 into 10 raised to 11 minus 5. 11 minus 5 is 6 Newton per meter square. Newton per meter square. So this is the thermal stress. So much of pressure. It experiences a pressure of 24 into 10 raised to 6 pascals on either side. Huge pressure. We can calculate what is the force. We can calculate the force. So, force exerted on either side. On either side due to closed ends, closed rigid ends. So, F is equal to 24 into 10 raised to 6 into area. Area of cross section is given here 40 centimeters square. So that becomes 24 into 10 raised to 6 into 40 centimeters square. Centimeter square converted into meter square, it becomes 10 raised to minus 4. 10 raised to minus 4 meter square. So thus it becomes 24 fours are 96. 960. 24 fours are 96 into 10 raised to 2 Newton. So force exerted is of this much strength, or 96,000 Newton. 96,000 Newton is being exerted. 96,000 Newton. Almost, you can say, if you round it off, it comes out to be almost 10 raised to 6. If you take 100,000, so 100,000 if you take it, it is going to be 10 raised to 6, almost 10 raised to 6, approximately 10 raised to 6 Newton. So much of huge pressure it will be undergoing, so much of stress it will be experiencing as a result. If the rail tracks, if the rails are not provided with the gap, required gap, then they exert such a thermal stress, such a high thermal stress, even just for 10 degree rise in temperature. As a result, due to their thermal stress, they tend to buckle. They tend to buckle up, and that will lead to very risky and dangerous accidents. Okay, this is the importance of thermal stress experienced by the metallic rods. Okay, now we'll solve one example of thermal expansion. Let us quickly solve a problem, very interesting problem. A blacksmith fixes iron ring on the rim of the wooden wheel of a bullock cart. I have drawn wooden wheel of a bullock cart, and this is the iron ring to be fixed at the rim of this, at the end of this wooden wheel. The diameter of the ring is 5.243 meter. and the diameter of iron ring is 5.231 meter. 5.231 meter. This is iron ring. At room temperature, say 27 degrees Celsius. At temperature 27 degrees Celsius, diameter of the ring is slightly less than diameter of the ring of wooden wheel. 5.243 meter, and this is 5.231 meter. If you take the difference, you see it is a difference of about 12 millimeter, 1.2 centimeter. Okay, 12 millimeter, or you can see yes, 12 millimeter difference is there. 3 minus 1, 2, 4 minus 3, 1, 12 millimeter difference, 1.2 centimeter. To what temperature should the ring be heated so as to fit the rim of the wheel? To what temperature the ring be heated? This will be heated very strongly. It will be heated very strongly. It will be kept. It will be heated very strongly. Okay, it will be heated very strongly, red hot, and then this wooden wheel will be fixed on this, so that when it is heated very strongly, you see it undergoes thermal expansion. Before it gets cooled down, this wooden wheel will be kept here, fixed here, and then it will be poured with water. When it is poured with water, suddenly it cools down and contraction takes place. Due to cooling effect, contraction takes place. Due to heating effect, expansion takes place. That is the application of thermal expansion. So initial temperature is 27 degrees Celsius. Initial length, let us take initial length as L1. L1 is equal to the diameter of the iron ring. Diameter of iron ring is 5.231 meter. And final length after heating. Final length after heating must be equal to the diameter of this wooden ring. Final length L2 equal to 5.243 meter. Now, the thermal coefficient of this iron ring is given. Coefficient of linear expansion of iron ring is given. Alpha L is equal to 1.2 into 10 to the power of minus 5 per Kelvin. 1.2 into 10 to the power of minus 5 per Kelvin. So using this, you are asked to find out what is that final temperature. T2. In degrees Celsius. So we will use the equation of alpha L. Alpha L is equal to delta L by delta T. Delta L by delta T. So delta L therefore is equal to L alpha L into delta T. Now delta L can be written as L2 minus L1. Therefore L2 minus L1 is equal to L is nothing but L1, initial length. L1 into alpha L into change in temperature. Change in temperature will be written as T2 minus T1. That is the equation. So we know the final length, we know the initial length. We are asked to calculate what is T2. T1 is also known, alpha L is known, L1 is also known. Right? Therefore, I can write the same equation here as therefore L2 minus L1 by L1 is equal to alpha L into T2 minus T1. T2 minus T1. So L2 minus L1, take the difference. It becomes okay. Even we can take alpha L also to the left hand side. So thus it becomes L2 minus L1 divided by L1 into alpha L is equal to T2 minus T1. So we can calculate T2 minus T1. Later on we can calculate what is T2. So substituting what is L2, 5.243 minus 5.231 whole divided by 5.231 into alpha L 1.2 into 10 raised to minus 5. This is equal to T2 minus T1. So you can check now. So I will take out this. So now we are left with taking the difference 3 minus 1 2, 4 minus 3 1, 2 minus 2 0, 0.012 divided by 5.231 into 1.2, 10 raised to minus 5. I will take it to the numerator, so it becomes 10 raised to 5. This becomes T2 minus T1. Using the calculator, you can calculate. You see, this can be calculated. Directly you can cancel this. So if you calculate using calculator, this comes out to be 0.00191 into 10 raised to 5 is equal to T2 minus T1. T1 value we know. T1 value is 27 degrees Celsius. Okay. T1. So thus I can write this same thing as, after cancelling with these zeros, I can write directly. Therefore 191 is equal to, so this is as good as 191 into 10 raised to minus 5. 191 into 10 raised to minus 5 into 10 raised to 5. So 191 is equal to T2 minus 27. 27 is the initial temperature. Therefore, T2 becomes equal to 191 plus 27. So it becomes 280 degrees Celsius. 280 degrees Celsius. So the temperature to be raised for this iron ring to be heated such that the temperature should reach 218 degrees Celsius from 27 degrees Celsius. Okay. So the difference in temperature is 191 degrees Celsius. Okay. So this example is interesting and application level example. So in the next video we will start discussing about specific heat capacity. Thank you. Have a nice day.